Welcome to YouTube Chem 237 Chapter 1 now. So we're going to begin by saying welcome to the fascinating world of organic chemistry. Whether you're here out of curiosity, gearing up for an exam, or simply looking to understand the molecules that make up life itself, you're at the right place. Imagine unlocking the secrets of how your favorite perfumes are made, how life-saving drugs are developed, or even how you digest your own food. Organic chemistry is like a hidden language of nature. And starting today, we are going to decode it together. Get ready to dive into a subject that's not just about memorizing structures, but about understanding the very foundations of life and the world around us. Let's explore this amazing journey together where molecules tell stories and chemistry becomes more than just science, it becomes an adventure. Our motto is always to challenge complexity and discover the simplicity within. A key idea we should talk about before we begin is that structure determines function. Structure determines function. This is an important concept that comes up in regular chemistry, but it is especially important in organic chemistry. Before we begin OChem, it is important to establish some foundations, and in this recording, we'll be doing just that. Let's begin by talking about the most relevant elements in the organic chemistry and their periodic trends. So let's dive in. To start, obviously, there's carbon. Carbon is the backbone of organic chemistry. If not all, molecules you look at in organic chemistry will involve carbon in some way. The next one is hydrogen. It is called the versatile mover. It often moves around and it's used everywhere. Oxygen is an important one. Nitrogen is an important one. Boron is an important one. Something interesting about nitrogen is that it's what started everything, like at all. Everything began with nitrogen. So let's talk about it. So Frederick Wohlher in the 80s, what he did was he took ammonium cyanide, which is NH4 and CO, and used heat and converted that into ether, which is NH4 and CO. So this is ammonium cyanide, and this is urea. So you might be wondering what's different. He didn't do anything, he just heated up a compound. But the very interesting thing is this is inorganic. This is organic. This is where the term majorly organic comes into play, and this is the emergence of organic chemistry altogether. So if you hate organic chemistry, Frederick Wohlher is the guy you want to blame. Other elements that are important are silicon, aluminium, phosphorus, sulfur. You also have lithium, beryllium, sodium, magnesium, potassium. Sorry, I marked calcium, potassium. Yeah, and pretty much most, if not all, the halogens. But the majority ones that usually involve fluorine, chlorine, bromine, and iodide. So these are all the relevant elements of the that you would need to know. Uh, for organic chemistry. I mean, you also need to know like noble gases, but I mean, mostly for the configuration, which we'll cover later. I'm just gonna erase this. Now, talking about the periodic trends, we're gonna start with electronegativity. Electronegativity. As most of you might know, electronegativity is the measure of the atom's ability to attract and hold on to electrons in a chemical bond. The higher the electronegativity, the stronger the atom pulls shared electrons towards itself. Um, so as you move from left to right, this electronegativity increases. And as you go from down to up, it increases. So the general trend for electronegativity would be something like this. I'm gonna erase this. The next one we're going to cover is to do it in a different color. Why not? The next one we're going to do is electron affinity. Oh, the affinity with the blue. Very nice. Electron affinity refers to the energy change that occurs when an atom gains an electron. High electron affinity means an atom releases more energy when it gains an electron, indicating a stronger attraction of additional electrons. So If you think about it, right, if you're attracting more electrons, you're going to like to take those strong electrons and release more energy. We know that releasing energy is an exothermic reactions, and exothermic reactions are usually better. They're spontaneous and just in general better reactions, right? So having a good high electronegativity kind of implies good high electron affinity. So thinking about that, they obviously share similar traits. So moving from left to right, you increase electron affinity and you increase your electron affinity as you move up. The next one we're going to talk about is ionization energy. Energy. Ionization energy is the energy required to remove an electron from an atom in its gaseous state. Atoms with high ionization energy hold on to their electrons tightly. This is again building up another layer. If you are very electronegative and you attract and you hold the electrons in a chemical bond, you're less likely to let them go. So if you have high electronegativity, it is probably the same thing. So you have a high, sorry, I should draw the general trend out for um, electron affinity as well. So as I was saying, if you have a high electronegativity, you probably have a high ionization energy and you share similar traits. So the trend would also be very similar. So going from left to right, ionization energy increases. Going from down to up, ionization energy increases. So again, the general trend is something like this. Now, for the contrarian of the group, I would say is atomic radius. What I mean by contrarian, it is the only one that goes in the other direction. So as you move from left to right, it decreases. So it increases as you move from right to left, and it increases as you go down. Now, atomic radius is just the distance from the nucleus to the outermost shell of electrons. So your valence electron shells, and it decreases as you go towards it increases as you move towards the left. So it's the only one that points in the opposite direction. That's pretty much why I call it the contrarian. Anyway, moving on, you can see that the electron plays a very important role in determining these periodic trends. So what is electrons? Electrons, especially valence electrons, are more important in this case. But what are valence electrons? I'm so glad you asked. Valence electrons are the outer shell electrons. Valence. Yes, Valerian? Yeah. Valence electrons are the outermost shell electrons. Many elements can gain them or lose them to reach the coveted octet. What is the octet? Octet is the noble gas configuration. Noble gas configuration. What is it? Octet usually implies having 8 electrons in your valence shell electron. So drawing out your whole element, let's take boron, right? So this is your protons, these are your neutrons, and then your electrons would be something like this. So you got 2 here, and you got 1, 2, 3. So these are your valence electrons. And boron would like to share these 3 electrons with other atoms to reach a noble gas configuration, which means it would have 8 electrons in its octet. So you can, based on how many you have, how many electrons you have in your outer shell, you can guess whether they would gain or lose the electrons, right? The noble gas configuration is the most stable form an element can be, and that's why when you move towards stability, you want the noble gas configuration. So, how does an element reach its noble gas configurations? It shares its electrons. So, to reach the octet or the noble gas configuration. The octet the elements share their electrons. And this sharing of electrons is called a covalent bond. Sharing of electrons is called a covalent. Sorry, I spelled that wrong. Covalent bond. Now, to understand how electrons are shared, oh, here's the meme. It's coming up. Now to understand how the electrons are shared, we need to know where they are at a given time. But due to Heisenberg's uncertainty principle, we can only, well, simplify it down. We can only know either how fast they're going or where they are. So to understand how where the electrons are, we work with probabilities. We work in to find electrons' locations. We work in probabilities. So an orbital would be a three-dimensional space. Let me just draw it differently. An orbital is a, let me draw the axis first. I think it'd be better. One, two, three. Oops. So the orbital is a three-dimensional space of the possible location of where the electrons can be. It basically tells you the wave properties of electrons, the wave properties. This is the orbital, by the way, orbital. I think I said the wave properties of electrons. Orbitals use the wave properties of electrons, so how fast they're going and what's the like where they're moving, and that tells us where their location is going to be. So this is an orbital. An orbital has a node, which means a node is a place of zero probability of electrons being there. Nodes have zero probability. Ability of electrons. Should stop changing colors that often. And so how do we write these orbitals out? Naming the orbitals, we usually have three major like numbers. So we have N, we have L, and we have Mi, which is this is your, and these are quantum numbers that help us determine the orbital's quantum number. So N is your principal, Qn, which is quantum number. I'm not gonna write this thing down. This is your angular momentum, Qn, quantum number, and this is your magnetic Qn, your quantum number. So let's take, for example, right, let's take hydrogen for an example. I think it'd be the easiest. We usually denote it as 1s1. 1 is your principal number. 1 is your principal number, and your angular momentum is given by 0 to n, right? So if your principal number is 1, then your angular number would be 0. And these angular momentum um, quantum numbers, 0, 1, 2, these basically tell you the orbitals which they can be in. So 0 is spherical, so spherical orbital or s orbital. 1 is usually your dumbbell, which is your, this is where usually this is your dumbbell. This is p orbital or your dumbbell orbital. And dumbbell. And 2 is usually the d orbital, but we don't talk about it that often. But it looks something like this, where you have three-dimensional space. And these can be in x, y, or z direction. This could be your pz or px. I said pz while saying px, but yeah. This could be your px, this could be your dx, this could be your sx, something like that. So these are your orbitals, and the magnetic quantum number basically gives you the spin, which goes from negative L to L, right? And that tells you the spin of your electrons. Um, so so this is basically how you write orbital configurations. And so the general trend usually follows. I have a table for it. So let's just so we have the general trend, as you can see here, trend is pretty much 1s2, s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 3d10, 4p6, dot 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 dot. Right, so you can look at the graph for the. Now let's do some examples. Well, let's do hydrogen, simple one, 1s1. Helium would be your 1s2. Your boron would be 1s2. Since you can only hold 2 electrons in your s orbital, you have to move on to the next one, which would be your next principal number, which is 2. So 2s2. But you still have 1 electron left, so you have to move to the next suborbital, which is 2p1. Then moving on to carbon, we have 1s2, 2s2, 2p6. Right? So so when you grow, for your angular momentum quantum number grows, you have more like different locations of electrons, right? You're only spherical here, now you're moving into a dumbbell, so you have up and then you have down, you have different like possibilities. With d orbital, you have even more, right? Up, down, left, and right, basically different like spots where your electrons can be. And so that opens up different possibilities of like regions. Another way of representing this is in a table format, which is your electron configuration table. So this one is your energy, your y-axis is your energy, and your basically on the same axis you have, this is low energy, this is high energy. In the same axis you have your different orbitals, so 1s orbital, 2s orbital, 2p orbital, 1, 2, 3, 3s orbital, 1, and 3p orbital, which is 1, 2. We usually won't go up 3p in UW237, but I mean it's important. So to draw an electron configuration in this table format, there are some rules you have to follow. So the first one is Aufbau principle. Uh, uh, Principle. This is principle, which basically states you have to start filling electrons from energy, low energy, to high energy. The next one is your Hund's rule, which is basically you have to fill each orbital before pairing. Fill each orbital to the max, I would say, to the full or like to the max before pairing. And then you have Pauli exclusion principle, which basically states always have opposite spin on the electrons. Now let's take carbon, for example, and then let's fill these out, right? So we have carbon. Carbon is 1s2, 2s2, 2p, 2. Oh, there's not, I don't know why it would be 6. So starting here, let's draw out our line energy. So first is 1s, right? So the 1s has 2 electrons. So first we have to follow the Aufbau principle, which is we start at the lowest layer, which is 1s, right? So we're starting off at 1s, and then we have to follow the Hund's rule to make sure we fill each orbital to the max before pairing. So since this can only hold 2, we put 1 electron here, and then we have to use Pauli's exclusion principle to make sure that we're giving it opposite spin. Opposite spin is usually up and down, not left or right, so we can't really draw this in any of our diagrams for electron configurations. So moving on to the next one is 2s. I'm just gonna, this just it fills up 3p. The next one is so moving on to the next orbital, we're gonna fill it up again, following the up principle, starting from low energy to high, right? So we started off at 1s, now we just filled up 1s, and we're gonna move on to 2s. Then we're gonna make sure we follow the Hund's rule, making sure that each orbital is filled to the max, and then start pairing them. So once 2s is filled to the max, we can use the Pauli exclusion principle to make sure they have opposite spins. Now moving on to 2p, we're gonna first start making sure the orbital is filled to the max, but we ran out of electrons, right? So these ones are unpaired electrons, while these ones are paired electrons. So sometimes you will have unpaired electrons in your electron configuration chart when you draw it out like this. So now that was a huge tangent. Going back to covalent bonds. I don't know why I keep messing it up. Covalent bonds, right? Once when you form a covalent bond, when you form a covalent bond, these idealized orbitals, like the S, the P, these idealized orbitals usually just mesh into one. Smash into one. And so they start looking something, why can't I move it? Okay, start looking something like this. They're just like, instead of having individual atoms, the clouds just move in together and they become this one whole blob of the molecule, as you can see in this example. So to help our minds grasp how they look, we usually use Lewis structures. I'm sure you have covered Lewis structures before, but I feel like I should just go over them really quickly. So Lewis structure is basically something like HF, right? These are your bonded electrons, right? There's 2 of them here, and then you have to draw the other valence, the outer shell electrons, or the valence electrons like this, right? Valence electrons. I'm going to do a quick example following all the rules of Lewis structure. Let's start with C6. Let's start with C6H6O, right? This is ethanol. Right. First, we start by counting valence electrons. Right, we get 6 from carbon, 6 from the other, sorry, I don't know why I wrote C6 from the other carbon, and 8 from the oxygen, giving us a total of 20 electrons, right? Next, C6860. I don't even think that works. I'm sorry, I messed up. So C2860, right? That's ethanol. So and then we have to pick the least electronegative element as our center one, right? So the least electronegative one here is carbon, following the periodic trans. Since we have 2, we can just put both of them in the middle, right? Then we start creating our bonds. And each time we create a bond, we have to make sure that we realize we have used 2 electrons. Right here, now when we have placed the O and the H, we first have to make sure, see, we cannot do this because this would break the octet rule. So we always have to follow the octet rule when making the Lewis structures, because this would give hydrogen more than 2 electrons, it would give it 4, but it only wants 2. And then this one would make sure oxygen won't have enough electrons. It will only have 7 instead of the 8 that it needs. So what we will do is we will put first oxygen here, and then we'll put the hydrogen, right? Then we put all the valence left, and we count the next step is to count all the bonded electrons. So we have 1, 2, 3, 4, 5, 6, 7, and 8. That gives us 8 times 2, which is 16. That leaves us with 4 electrons, and we just put them on oxygen because it needs valence electrons. So this is how you draw a Lewis structure of ethanol. Next, before we move on, it's important to make sure that we have a full octet in all your different elements and all electrons have been placed. So in this example, you can see the first carbon has 8 electrons, 2, 4, 6, 8. I'm gonna move it so it looks separated from the bond. The second carbon also has 8 electrons, 1, 2, 3, 4. So 8 electrons, and your oxygen also has 8 electrons, so 2 bonded and then 4 valence. And then hydrogens only need 2, so you can see it's bonded everywhere, so you have your valence electrons. That was basically your Lewis structure. Formal charges are a part of your Lewis structure as well. Formal charges, so let's move on back here. Formal charges usually are calculated by the number of valence electrons minus the number of H, number of bonds, minus number of non-bonding. This is basically to see since when everything fuses together, right, it becomes a big molecule, but we need to know what the individual element is contributing. So we have formal charges. So B, for example, your BF, your borium tetrafluoride has a negative charge, right? The negative 1 charge. So what is contributing to that negative 1 charge? If you draw out borons, if you draw boron, right? Boron makes, this is tetrafluoride, right? The negative. Boron was an exception to the octet rule, which I didn't cover exactly, but basically boron only makes 3 bonds. In this case, it's making 4, right? So if we apply the formula, right, number of valence electrons that boron has are 3. It's making 4 bonds here, and number of non-bonding electrons is 0, so it has a formal charge of -1. So in this case, boron is what's contributing to the negative charge of the entire molecule being -1. Another thing we have to cover with Lewis structures is bond length. Bond length is just basically how much sharing, how the different, like the distance between two elements in a bond, right? So basically, as you increase the number of bonds from double bond to triple bond, right? What happens to the bond length? It decreases bond length. Another thing, the more electronegative the difference gets, the more electronegativity difference there is, the bond length also decreases. So from here, 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 the bond length is decreasing. Basic trends. I think I've covered this in organic chemistry or regular chemistry as well. Um, the next thing we have to talk about is bond angles. Bond angles, the ones that are important that we need to know are linear, which is usually CO2. Then you have bent. Oh, sorry. HOH, which is your water. Then you have trigonal planar. Which looks like this. This is borine trifluoride with many charges. Then you got your trigonal pyramidal. What can I spell? Pyridol, which looks like NH3, ammonia, right? Ammonia, NH3. Basically, why it's trigonal pyramidal is if you ignore the double bond, it looks something like this, where you have triangle and then a pyramid form. So this is why it's called trigonal pyramidal. Just for those people who, this is your nitrogen. These are your three hydrogens here. So it's a 3D shape. Then you got tetrahedral. It's gonna come up a lot. Here's your methane, your best friend, which looks like this. Oh, by the way, a good way to draw tetrahedral is you draw two L's with your hand like this. Imagine this is your hand, right? This is your other hand, right? You turn this hand like 90 degrees. So now your hand looks something like this, and your other hand looks like this, right? And then, wait, so this hand, back, like this hand is facing outwards, right? And then you like stick them together, and then it becomes something like this, where your first thumb is this way, right? And you have your big hand, like this hand's in the back, and then you have your like right. So you this is your. I mean, it's really hard to draw it in 3 dimensions, but this is basically your H. This is your C. This is your H. This is your H, and then this one's going in the back. So this is your H. So that was a small tangent on how to draw tetrahedrals with your hands, but I mean, that's up to you. So, what determines these bond angles? I'm so glad you asked. Is hybridization. This is where this picture comes into play, which I'm going to move a little bit. Say totally estimated wrong. Where's would lie? This is then the meme I made. I hybridize. Hybridization is orbital overlap. Overlap. Orbital overlap is basically when you have your hydrogen, right? It's 1s form, 1s1, right? What does that look like? It looks something like this, right? Where you have your spherical hydrogen in the center and an electron surrounding it with the spin. Right now, if you make H2, right, where you make a single bond with hydrogen, you take another H with the opposite spin, right? And then you pair them together, and then it looks something like this. Negative, you got positive, eight, oops, here, that's there. Now you can see this overlap is called this is the orbital overlap, which is the sigma bond, which is why sigma bond has been shown. Sigma bond, which is the bond of single, like when you make a single bond, you have a sigma bond basically. This is the orbital overlap. So this is S. This is where the hybridization comes into play. So we can also show it in terms of so e so how does that work with bigger elements, right? Let's move on to some other bigger elements. Let's say carbon, right? Carbon has 1s, you got 2 electrons, you got 2s, you got 2 electrons, and you got p with 1 paired electrons, right? So, but we know very well that carbon can make 4 bonds, right? So with only 2 pairs of unpaired electrons, how does carbon make 4 bonds, right? It has 4 valence electrons, but only 2 unpaired ones. So how does it make bonds? What it does is it takes its 2s orbitals, right? This is very interesting. It combines them and forms a sp3 hybrid orbital, which is closer. It's very important to see where the distance is from the s orbital, right? So s orbital doesn't change, but your 2 orbital becomes your sp3 orbital, right? Now this hybrid orbital has 4 unpaired electrons, and now these can make sigma bonds with a hydrogen. So something like this, where your sigma bond plus your pi bond, or your sigma orbital, sorry, your s orbital and your p orbital, I was getting ahead of myself, sorry, come together to make a hybrid sp3 orbital, which looks something like this, right? And so your carbon has 4 of those C. I'm gonna just draw it off. 1, 2, 3. And this is where your shape comes from. So this is where the tetrahedral shape comes from. Now it can take the s orbital of a hydrogen with an opposite spin. So this is downspin, this is upspin. I'm assuming these are all downspins. This goes downspin, downspin, and then it finds hydrogens with an upspin, and then it makes the orbital overlap, which makes your sigma bond. So you got C with the orbital overlap. I gotta draw it up first. H. And I keep switching them around, but I guess it makes sense. So this is your sigma bond. Right, and then you just have to draw it up 3 more times. I can do it. Whoops. You got that done. Up. You got H. You got C. So you got this. And you got that. This is your sigma again. Same thing here. Down. Sorry, whoops, I keep making the same mistake. Down. Up. H. Right, you got this. And you got that. This is your sigma bond. And then just one more. So you got your down. You got your up. Sorry, it's weird. Down. Up. H. Here. Right. Overlap. Overlap. And these are your sigma bonds. Right, so this basically just equates to your CH4. This is how you do, this is how a sigma bond comes into play, right? Now you can have, let's move on to something a little bit more complex, right? A little more, I spelled a little wrong. Little more complex. These are alkenes. Alkenes are CC double bonds, which we'll cover later, but alkenes are CC double bond. And what if you want to draw something like this, right? When you make a double bond, you have pi bonds come into play. And I'll explain what those are later. So if you have something like this, how would that work with the orbitals? All right, so you have your carbon, 1s, 2s, 2p, boom, boom, and then boom, boom, right? So instead, now you're just making 3 different bonds, right? If you look at just this carbon in isolation, it's only making 3 different bonds. So how does that carbon do that? So what it does is instead of taking the entire p orbital, the s and p orbital just combine parts of it. So in this case, you just combine with 1/2 of the p orbital. So in this case, you make an sp2. So you have sp2, which looks like this. 1, 2, 3. You got your p orbital up above. I think it's very important to see how, in terms of energy, it's different. Like, look at the space, the distance between a 1s1, sorry, 1s, and then 2p, sorry, 2sp2 hybridized orbitals. Like, I think this gap should tell you which one is more lower in energy and which one is more higher in energy. I think it's very important and it comes into play a lot of times. You still have your 2p with 1 valence electron. So now what does this look like, right? So if you combine this again with only A1s, you got your s, and then you got your p orbitals. Oh, I should reshade this one in. Right, you make your sp2, which looks something like this. One, two, and three. This was your tetrahedral shape. Tetrahedral shape. This is your trigonal planar. Because you're making double bonds, right? So what in this case, what is happening is basically you have like valence electrons up here. So you have your third sp, right? And then you got your valence electrons here. So what this is doing is basically you're taking these p orbitals and they're making bonds. So in this case, what is happening is you're taking, so you have your three orbitals, you're going to take this, another carbon's sp3, right? And then you got sp2, sorry, misspoke. And then these pi bonds also make a bond. And this bond is called a pi bond. When just the p orbitals of your carbon make bonds, that's a pi bond. And so that gives you your pi bond. And based on this meme right here, you can see that pi bonds aren't as strong as sigma bonds because they're just based on small things, right? And then these are still your hybrid orbitals with H. I'm not going to draw the whole thing out this time. So these pi bonds are more important to understand. I'm making H, right? H and H. This is how you get your alkenes. So that's pretty much it. And then moving on to the third one, even more complicated. Hopefully not even more complicated, but I hope you're looking at the trend and seeing how that's all playing out. You'll see it becomes. So in this case, what's happening is carbon is giving even less. So the hybridization is even lower. So basically, instead, you're still hybridizing these, but you're just using the orbitals and not really any of the electrons per se. So you got your energy levels again. So you got your 1s, right? And this is your sp. And you just got one on here, and you still got your p orbital with three valence electrons, right? So now what does this look like? Wait, I messed up. Sorry, it's like this. Fixed. So how does this look? You only have your 1s and then your 1p, which gives you your thingy. So it just looks like this, where you got your thing and your thing, and then and so this is where your bent shape really comes into play when you only have two bonds. But in this case, what you're doing is you're making, when you have a triple, oh wait, I should have probably written it out. I don't know what to clear the canvas. So this looks like this, right? Now from here, what you're doing is you're making a triple bond. So you got two p orbitals now. And these two p orbitals are making bonds in a different dimension. Well, this could be in your x dimension, or sorry, your y dimension. This could be your z dimension, where these two are making different bonds. And the rest is pretty much normal. So you have your H here, and your H here. So these are your sigma bonds, and you have pi bonds here, which looks something like this. Triple H. Now to simply summarize this all, a single bond has one sigma bond. A double bond has one sigma bond, one pi bond. A triple bond has one sigma bond and two pi bonds. And these hybridizations determine the shape of your Lewis structure. Now, doing a more complicated example of all of this is NH3. Like what happens when your electron is not involved in bonding? How does that impact shape, right? And this one, this is linear because it's straight. You're making double bonds, so it's linear. This one is trigonal planar. It's sp2 hybridized, by the way. sp2, this is sp3. Sorry, sp, not sp3. Whoops. sp, and then this is tetrahedral, which is your sp3. This one's sp3. Right, all right. So now moving on to this example, NH3, which looks something like this, where your H's are bonding, but you still have this lone pair. How does this look when you're making hybridizations, right? So you got your N, which looks something like this. I don't know why I keep doing it. So you got your 1s, 2 electrons. You got your 2s with 2 electrons, and then you got your 2p with 3 electrons. 1, 2, and 3. Right? So when you make an sp, then you make your sp orbital, your sp3. This is also going to make an sp3 orbital. You have your sp3 orbital has 5. The sp3 orbital will have 5 pairings, right? So 1, 2, 3. I'm sorry, you have 4 sublevels. So you can have 1, 2, 3, 4, and then one of them is paired up. So these are your paired electrons, which you can see here. So how would that impact shape, right? So you got your so you got nitrogen with its paired electrons, right? And then you're mixing what? Right, so you're mixing your s and your p orbitals, right? Your p orbital. So you get 4, but one of them is paired electrons. So it looks something like this. Paired electrons, your n, while the rest look like this. 3 unpaired ones, your electrons in here. And when you make those hydrogen bonds, H, and your H here. Sorry about the drawing degradation, but basically here's your H bonds and it looks something like this, right? And so this is trigonal pyramidal with your electrons. So this angle is 107, this angle is 180. Sorry, I should probably, this angle is 180, this angle is 120, and then this angle is 109.5. So this is what determines your bond angle. This whole shebang can help you determine your bond angle. And I have this neat little diagram for you guys, or this graph, which can help you out with number of bonds, like number of bonds you're creating, or how many you can make. And based on that, you'd have a lot. So the important ones to remember here, I would say, are linear, trigonal planar, tetrahedral, uh, angular, bent. Bent is very important. Trigonopyramidal and bent from trigonopyramidal. These show up a lot, but the other ones are can show up as well. But these ones are usually in phosphorus or sulfur or something like that. So T-shape or like seahorse and all these other ones, they're covered, but not as in depth in organic chemistry because we don't have a lot of sulfur and phosphorus molecules. Or we have a lot of phosphorus, like ATP and stuff, but like not in terms of well, it won't be a lot in your organic chem journey. So this is basically everything we have to know about Lewis diagrams. So a lot of it um, is like hybridization. I kind of sped through it, but I think it makes most sense, right? Like you combine your s and your p orbitals to make a bigger hybridized orbital, your sp orbitals, which are a combination of your s and your p. Um, and then you can use that to create individual bonds with hydrogen. And Pi bonds also basically you have when you don't need as many electrons, you leave some in your p orbitals, and p orbitals are empty, so they can make pi bonds. And then I want to make sure you know the distinction between a pi bond and a paired electron um, in an sp3 orbital. Pi bonds are both, as I would like to point out these. Okay, let me just use a different color. Hopefully that makes more sense. I think this tripped me up a lot when I was in like when I was taking this class as well. So these are your pi bonds, which use p orbitals, right? And this paired electron is just here. I would like to point out these have two layers, both layers make bonds. And that's why double bonds cannot rotate, because you cannot rotate these like bonds, because if you rotate, they'll break, right? So you cannot rotate these bonds, hence you cannot rotate your pi bonds. And so it's even harder to rotate a triple bond. But with your paired sp2, it's just one like big ball up of all your electrons. They're like in this one position instead of being spread out into different spins, right? So you got your two here and then only one here. So that's a big difference. You need to just understand. There's something called bond order you have to cover. I think, this is molecular orbital theory, which basically like is an expansion on a little bit on the or like hybridization stuff. So bond order basically will move on into resonance. Resonance is a very important topic in organic chemistry, comes up a lot. So bond orders matter for resonance and stuff. So in your molecular orbital theory, right, your hydrogen bonds. Remember when I was talking about the spin? I think the spin comes back here. So the spin, you can have two hydrogens with same spin, right? So but these won't pair together because of the Pauli exclusion principle, but these would, right? The opposite spin guys would pair together. I should probably just stay consistent with my drawings here. So something like this. Right, so these would make a bond because they're opposite, but these won't. So to denote this in energy wise, right? Because remember earlier when you're making a bond, you usually release energy. It was a part of ionization energy, right? So, but that energy cannot just go somewhere, right? So you have to have bonding and non-bonding orbitals. So when you make that anti-orbital like bond, I think I gave it away with the anti-bonding, but like I think that makes sense. So this being your anti-bonding orbital. Is your anti-bonding orbital. I spelled bonding wrong, but anti-bonding is your H. And then this is your bonding orbital. Right, so based on this, how many different, based on how many different bonding orbitals you have, you can have different amounts of bond order. But something important, like for example, it's the same delta G, like the delta G. I'm sorry, wait, just here, this delta G and this delta G are the same. I think delta G equals delta G, and it's stupid, but I should probably write it out. Um, yeah, so this is molecular orbital theory, which gives you bond order. So like a single CH has a bond order of 1. C double bonded to a C has a bond order of 2, and a C triple bonded together has a bond order of 3. Right? This is based on your molecular orbital theory. I don't think these relate that well, but it's important to just know like this distinction. And so now what I've been hyping up for like past minute is resonance. So what is resonance? Resonance is a big important topic, one of the most important topics in organic chemistry. So I'm going to slow down here and explain. It explains a lot of organic chem behavior, and much of it boils down to this. But resonance is basically how the electrons are shared between the molecule. I think that drawing back here. is very important. You know how it becomes this blob of like electron space where all the electrons are just shared together and it becomes like this one blob. So holding an electron at one position is very important. This note is very important. I should probably write it down. Holding an electron at one spot is energy intensive. And so most molecules don't want to do that. So when they create this space, right, they are willing to share the electrons around, and this sharing of electrons creates a more stable, like delocalization of charge. It basically creates us like creates stability because it decreases the amount of energy required, right? So so since you don't want electrons at one spot, what you do is you delocalize these electrons. I will show that really quickly, delocalization of electrons, which decreases energy and makes you more stable. What this means is, let's take ozone for example. Ozone looks something like this, right? Better make that one for more chocolate. I'll draw the electrons right now. 1, 2, 3, 4. 1, 2, right, 6. So this is where the negative charge is coming in, right? So what the negative charge right here, and this makes this whole thing negative. So what ozone can do is one thing, right? It can hold the negative charge at the specific oxygen, but that's very energy intensive. So instead of doing that, what it does is it delocalizes charge. These are arrow pushing mechanisms. They come up a lot. So what it can do is it can delocalize the charge, which is move this electron around, which this arrow configuration is showing, and give it to the other oxygen. Let's say this is oxygen 1, 2, and then 3, right? So it can move the electron from oxygen 2 to oxygen 1. So it looks something like this now. We have 1, 2, 3, 4, 5, 6, negative charge here. This guy's still with its double bond. I'd move this electron, and now this guy has the negative charge, right? So again, holding this electron here is energy intensive. So what we like to say is this is a dragon. These are both mythical creations, right? So dragon, and this is the unicorn formation, formation or form, right? Form. I'm just gonna say form. We can say formation, form, and this is the unicorn form, right? But the real form, right? Dragons and unicorns, one horn. You can like interchange between this is actually this, right? We use dashed arrows to show how there's transference of the electrons. So this is actually the natural state of ozone. This is what we wouldn't see if we just grabbed ozone somehow. We wouldn't see ozone in this dragon form or this unicorn form. We would mostly see it in this state where electrons are constantly being shared. So in this rhinoceros, like the rhino form, this would be where the electron is being shared. The formal charge is still negative, but since the electrons are being shared between both, they both are partially negative. This is what the partial negative sign means. So this shows how they're moving, right? And in terms of energy, if I draw this in a graph, right, you have your high energy states and your low energy states. So this guy, let's say it's 1, this guy's state 2, this guy's state 3. And so the dragon and the unicorn are actually resonance forms your of the ozone layer, and rhinoceros is the real form. So your dragon, let's say this is your dragon form, which means this guy, right, with all the negative charges and everything, is your dragon. This is your rhinoceros form. And this is your rhino form and your unicorn form. Could be this guy with the negative charge and this guy neutral. In terms of energy, since you're holding the electrons at one specific element, your higher energy. This is energy again. Yeah, this is high energy positions. These are low energy positions. This is your unicorn form. And the dragon and this unicorn is the resonance structure of ozone. So these are the resonance forms of ozone. Um, Another aspect of resonance would be, I guess, benzene. Benzene is this benzene, right? This would probably be explained further in a later chapter, but just to cover the basics right now. Another thing benzene can do is, sorry, this is correct, where you have your things spread out. So what it does is it basically, the double bond can move around and give you this. So this is your dragon form again. This is your unicorn form. And this, the actual form for benzene, is often denoted as this. Or you can like say like, I mean, so you can see how the benzene rings can move. So sigma bonds and pi bonds can also be involved in resonance. So these are all different resonance structures of um, benzene. This is benzene. Let me label that as benzene. So to recap, what did we just cover up, right? So we first did elements, right? Elements, then we talked about periodic trends. Next, we covered the electron, right? Valence electrons. How we see valence electrons is to orbital. So we did orbitals, right? We did naming, did the N, L, and Mi, right? Then we moved on to configuration, the orbitals, and then the naming with the 1s2, right? Then we did from there we moved on to Lewis. Wait, I forgot I didn't write configurations as well, right? The diagram, electron configuration, orbitals configuration, diagram, which is the graph, right? Then from there we moved on to Lewis structures. We did how to for Lewis, how to. Then we did bond length, bond angle, which talked about hybridization. Hybridization, what else did we cover? We did resonance, hybridization, formal charges, right. Hybridization, bond length, bond angle, formal charges, and finally we covered resonance with bond order. I didn't actually talk about that. Wait, I'll do that resonance with bond order. Remember how we mentioned that if you had a single bond, you have a bond order of 1. If you have a double bond, you have a bond order of 2. But in this ozone case, right, you don't really have a single bond or a double bond, right? So what you have is a bond order between 1 and 2. So like your bond order isn't really 1, it isn't really 2, so it's in between these two. So your bond order here could be like 1.2 or something. This could be your bond order. And then different like sharing involves different like bond orders. Like sometimes double bonds are more shared in one spot than compared to others, and different examples you'll see later on. But basically, so if you don't have a single bond, if you don't have a double bond, then you have it's a bond order isn't 1 or 2, it's in between these two. It can be like 1.2, 1.8 or something like that. So that's basically what the bond order is. It pops up from time to time as in certain parts of the question. So it's important to know. Right. Another important thing we should cover is the sp2, sp stuff. So if given like a random, just a random element, right? Like C, CH, C double bond, C, H, O, H, 1, 2, 3, 4, right? So we should be able to tell, right, let me just change this. We should be able to tell the hybridization of each of these carbons, right? And the oxygen, but we'll just focus on the carbon. So this guy, since it's making 4 single bonds, we know it's an sp3. This guy is making 2 single bonds and a double bond, so this is an sp2. Same with this guy, it's making 1 double bond and 2 single bonds, so it's also sp2. And then this guy's making a triple bond, so it's an sp. So it's important to be able to distinguish this. Well, I'll post a video with practice questions. We'll cover all of this stuff. Thank you for watching.